So, welcome to a lecture series on advanced linear algebra. We have already seen for self adjoint operator defined over a finite dimensional inner product space, the space has a orthonormal basis consisting of eigenvector of the operator defined on that space. Now, we are going to see the answer whether similar answer holds good when the self adjoint operator is replaced by a normal operator. But before moving to that, let us see what we have already seen from our last results. As a corollary of my previous result, I can say like this: if A be a n cross n Hermitian matrix, that is self adjoint matrix, then there is a unitary matrix P such that P inverse A P is a diagonal matrix. That is, I can say the original matrix A, that is self adjoint matrix A, is unitary equivalent to a diagonal matrix. If the A is a real symmetric matrix, then I will say that A is orthogonally equivalent to a diagonal matrix. So, in that case the P matrix will be a orthogonal matrix and P inverse A P will be diagonal. So, let us prove these results, which is basically coming as a consequence of our previous theorems that self adjoint operator defined over a finite dimensional inner product space, that space has a basis, orthonormal basis consisting of the eigenvector of the self adjoint operator. Okay. So, let me consider, let V equal to say C n cross 1, the space of all column n cross 1 column vectors over the complex plane C, with standard inner product on C n cross 1, that is this one. Let T be a linear operator defined on V such that matrix representation of T with respect to standard basis for V is capital A. So, this implies that T is mapping from V to V, which is mapping x to Ax type. Now, since A is self adjoint, so that is A equal to S star implies T also equal to T star, T equal to T star, that is T is also self adjoint operator. So, this implies there exists an orthonormal basis, say B equal to, let me consider alpha 1, alpha 2, alpha n for the space V, that is C n cross 1, with alpha I is eigenvector of T and C I belongs to the corresponding field C such that T of alpha I equal to C I alpha I. So, this is true for I equal to 1 to n. Let the matrix representation of T with respect to this basis be equal to D, that is equal to C1, C2, and Cn, this is 0 diagonal matrix. Let P be the matrix whose first, second and nth column are alpha 1, alpha 2 and alpha n respectively. This implies that P inverse AP equal to D. Already we have proved that if a operator is diagonalizable and here alpha 1, alpha 2, alpha n the corresponding eigenvectors associated to eigenvalues C1, C2, Cn. So, then definitely if I consider the P is a matrix which columns are corresponding eigenvector, then definitely P inverse AP equal to D. Here P is unitary matrix, because here the alpha 1, alpha 2, alpha n are defined over the complex plane C. So, P is here unitary matrix. If A is real symmetric, then one can consider V equal to your R n cross 1, that is set of all n cross 1 column vector over the real line, and then proceeding exactly same way, one will get an orthogonal matrix P such that P inverse AP will be D, where D is diagonal matrix. Okay. So, we have seen that if a matrix is Hermitian or self adjoint, then it is diagonalizable. Now, let me consider the other situations. Other situation means now you want to drop the concept that operator is self adjoint. Now, if I consider instead of self adjoint simply normal operator, then what is happening? Okay. So, now we want to replace the self adjoint operator by normal operator. In this case, let us quickly check if we consider a normal operator defined over a finite dimensional inner product space, then if alpha is a vector in the space, and if alpha is a eigenvector of T, then with the eigenvalue say C, then definitely alpha will be also eigenvector of the corresponding adjoint operator with the eigenvalue C bar. So, let us quickly prove these results. So, this will be act the key factors to prove our next results, which is basically lead to our mission that if you consider normal operator on a finite dimensional inner operator space, this space will have a orthonormal basis consisting of eigenvector of the normal operator. So, let us prove these results that V be a finite dimensional inner operator space and T be a normal operator on V. Suppose alpha is a vector in V and alpha is the eigenvector with eigenvalue C if and only if alpha is an eigenvector of T star with eigenvalue C bar. Okay. We have for any alpha belongs to V, norm of T alpha equal to norm of T star alpha, because now inner product of T alpha equal to inner product of alpha T star T alpha, which is equal to inner product of alpha T into T star alpha. Okay, because T is normal, so T into T star equal to T star into T. So, I can replace T star T by T into T stars. So, this implies this quantity equal to inner product of T star alpha and T star alpha, since T star of star equal to T. So, that is why norm of T alpha equal to norm of T star alpha. Now, if alpha is a eigenvector with eigenvalue C, let alpha be the eigenvector of T with eigenvalue C. So, this implies T alpha equal to C alpha, T alpha equal to C alpha. In general, T minus Ci, in general T minus Ci star equal to T star minus C bar I. I mean adjoint of T minus Ci equal to T star minus Ci. So, this implies I can say using the previous results, norm of T minus Ci alpha will be equal to norm of T star minus C by alpha. For any alpha belong to V, norm of this will be equal to this quantity. So, this implies T minus Ci alpha will be equal to 0 if and only if T star minus C bar I alpha equal to 0. So, this implies alpha will be eigenvector of T associated to eigenvalue C if and only if alpha is eigenvector of T star associated to eigenvalue C bar. So, we have seen that under what conditions a non-zero vector of the space V will be eigenvector of the operator T, where T is a normal operator. So, let me define a normal matrix also. I mean, as you have defined self adjoint operator and self adjoint matrix, here also let me define normal matrix. And n cross n matrix B is said to be normal if B into B star equal to B star into B. So, a normal matrix is defined exactly same way the operator normal operator is defined. Here I am saying that B will be normal provided B into B star will be equal to B star into B. Okay. Okay, so now based on the definition of the normal matrix, now let me introduce one nice results. It is like this: suppose V be a finite dimensional inner product space and T be a linear operator on V and B be a orthonormal basis for V. Suppose that the matrix representation of T with respect to order basis B equal to capital A, which is a upper triangular matrix. Then T is normal if and only if A is diagonal matrix. So, the definition of normal matrix or normal operator will be more interesting if we have understand this ones. Otherwise, simply saying that A or T commutes with its adjoint will not make that much of impressive. We are not able to see what is the inside of these operators. But if you consider these results where I am showing that suppose there exists a orthonormal basis on a finite dimensional inner product space V such that operator is defined over that space and the matrix representation of the operator is a upper triangular matrix, then I am saying that T will be normal if and only if that upper triangular matrix has to be diagonal matrix. So, this is the most important results. If a normal operator is defined over a finite dimensional inner product space, then space has a orthonormal basis consisting of eigenvector of the normal operator. So, let us quickly prove these results. Okay. Let me prove the first if part, that is given A is diagonal, A is a diagonal matrix. This implies, I mean A star is also so a diagonal matrix. and A into A star equal to A star into A. So, this implies T into T star equal to T star into T. So, this implies T is normal operator. Now, let me consider the other way. Given A is a normal matrix, A is a normal matrix. So, this implies T is also a normal operator. It is given to us. Okay. Let B equal to alpha 1, alpha 2, alpha n be orthonormal order basis for the space V such that matrix representation of T with respect to this order basis equal to the above A. Okay. Because we know V is a finite dimensional space, we can have a orthonormal basis and the matrix representation of the T with respect to this basis will be suppose A, which is also normal because T is normal. So, this implies if you consider the image of T alpha 1, so this implies T of alpha 1 will be equal to, it is also given to me that this is the upper triangular matrix. This is an upper triangular matrix. Now, this is upper triangular matrix means A equal to of the form of A11, A12, A1n, 0, A22, A2n and ANN. So, this is the structure of the matrix A. Now, T of alpha 1 will be what? It will be A11 alpha 1 because the definition of the matrix representation of T with respect to order basis B says that the T of alpha 1 has to be basically A11 alpha 1 plus A21 alpha 2 plus AN1 alpha n, because since this is upper triangular matrix A21, A2, A31 all are 0. So, simply I will have A alpha 1 equal to A11 alpha 1. So, this implies what about the T star alpha 1, because our last result says that if see here it shows that alpha 1 is an eigenvector associated to the eigenvalue A11. Now, T star alpha 1 will be what? T star alpha 1 will be A11 bar alpha 1 according to our previous results. Okay. So, I am getting these ones, but according to definition of the matrix representations of T star with respect to B, if I consider A star, then T star of alpha 1 will be equal to sigma A star j 1 alpha j equal to 1 to n. Here matrix representation of T star with respect to this same order basis equal to S star. So, this is like this. So, this implies this is equal to sigma j equal to 1 to n A 1 j bar alpha j. This is second one. So, 1 and 2 implies, so 1 and 2 implies A 1 j bar equal to 0 for j greater than 1. I mean a bar 1 2 equal to 0, a bar 1 3 equal to 0 and a bar 1 n equal to 0. Okay. So, I have a 1 j bar equal to 0 for j greater than 1. So, this implies T alpha 2 will be equal to a 2 to alpha 2 only, since a 1 2 equal to 0. Why a 1 2 equal to 0? Because a 1 2 bar equal to 0, this implies a 1 2 also equal to 0. So, T alpha 2 equal to a 2 to alpha 2. So, this implies T star alpha 2 will be equal to a 2 2 bar alpha 2. I have gotten the previous results. Okay. So, then this implies a j 2 star equal to 0 for j not equal to 2. So, this implies a 2 j basically bar equal to 0 for j not equal to 2. So, this implies a 2 3 equal to 0 equal to a 2 4 equal to and a 2 n also. Similarly, proceeding in the same way, we can easily see that the matrix A is a diagonal matrix. So, what we see here is somehow if I can have the matrix representation of a operator with respect to some orthonormal basis is an upper triangular matrix, then the operator T will be normal if and only if that upper triangular matrix is diagonal. Now, this give a hints to show the existence of orthonormal basis for the space which are the eigenvectors of the normal operators. We are going to prove these results in our next class.